Hello community, so great that you are back. Yes, I have physics, this means science in my title. My goodness, what you gonna explore? Two papers I would like to show you here from April 10 here, the AI scientist, and accidentally this is a paper I had back in my mind and I said, okay, I try to combine it, no? And this is here by MIT, do two AI scientists agree? And at first I was looking at the first paper, I said, yes, hey, that looks interesting, no? There's now version 2 of the AI scientist, eliminate the human-authored code templates and novel progressive agentic tree search methodology. Yes, I said, okay, it is just part 2 of part 1. I have this video on part 1. So yeah, maybe. But you know what? The real surprise is this paper. What a beautiful paper. And they simply have a question, you know? As these AI scientists, quotation mark, begin to operate now autonomously, what the hell are they doing? So what is their scientific theory that they are gonna apply to solve the problem? Because it is nice to have the workflow of an AI scientist, you know, and then it builds an MCP protocol and has some agent-to-agent protocol, and we have multiple agents interacting with each other. But the core of the intelligence is, damn, what scientific theory are you applying to solve the problem? And here we have this beautiful idea by MIT. So let's open up and have a look. The paper begins by framing the problem and say, hey, imagine we have two AI models, no? Two AI scientists, and they are trained on the same physical data stream. Do they learn the same underlying mathematical theoretical representation, the same physical theory, or do they converge here on some distinct formulations? This we also have with humans, no? Newton versus Leibniz in the history. Two people had different ideas to the same topic. So they say, hey, we review now the methods here from symbolic regression to neural networks. We have a look at the Hamiltonian neural networks and the Lagrangian neural networks. And let's see if they can help us, yeah? Because what we want is, we want to extract from data the governing equation of nature, the law of nature. Yes, we want to do physics. Yes, absolutely. And if you are not aware, and I have not been aware, because imagine there was a time that this YouTube channel was not broadcasting. 2019, we have here from Google Brain, Hamiltonian Neural Networks, beautifully. And July 2020, Princeton University, Lagrangian Neural Networks. So this was right when the autoregressive, you know, GPT, I don't know, 2 or 3, was coming up. And they destroyed here this beautiful development. Because GPT-2 could write a sentence. But this here is physics. Look at this. Here we build about here the underlying symmetry. And in physics, the symmetry corresponds to conservation law for energy momentum. And yet, so neural network models see increasing use in physical science. They struggle to learn the symmetry. And they propose now the Lagrangian neural network, which can parameterize arbitrary Lagrangian using neural networks. And in difference to the old Hamiltonians, they have now a better idea. You know what? They did even this here with a relativistic particle, demonstrating energy conservation here, and even used it here for wave equation. AI was able to do this. Can you imagine? In 2020, before this goddamn OpenAI with this stupid GPT came along, and the whole hype moved away from physics to linguistic AI. We have here beautiful explanation in this paper. If you're interested here, and you have to study this a little bit if you want to follow here the video about Lagrangian mechanics, tell us here that the action functional here, beautiful, the kinetic energy, the difference here to the potential energy. Then we have here Euler-Lagrange equation. We're going to use parametric Lagrangian, and we can finally solve this here for a new parametric loss function. If you want to have the complete code to this, here we have the GitHub repo. We have everything and notebooks and everything special relativity here. With AI could solve special relativity. My goodness, what have we done in the last 5 years? No? Have we been asleep? Just writing here, I don't know, poems and emails? Where's science? But now we have a new study. Now we say, okay, MIT, we propose a new architecture. Multiple AI Scala scientist. And a scalar, if you know here, this is even less than a vector and much less than a tensor structure. So we go here for a simplification. We will work maybe only in a one-dimensional physical system to build up a new theory, to build up new single neural networks, to learn here diverse theories across multiple physical systems. They will train here this mass framework across different data sets, including here a simple pendulum, very simple equation of motion, the Kepler problem, beautiful, and some syntactic potential with higher dimensionality. And they will analyze here the activation in the last layer of our multi-layer perceptron that we will have here, and we will distill the theories learned here by mass. A little bit fast, never mind, we go in detail. Just give me here a second. So we want to here encapsulate the governing equation of the physical system that we provide the data to AI. And AI will find the physical laws, the equation of motion. But we will do this not just for one scientist. We will provide the data of multiple physical systems and tell the AI, hey, I've given you multiple physical systems, from a pendulum to some other systems to gravitational wells, even maybe to relativistic systems. Now find the physics, find the mathematical equations. Now you know that neural networks in general are universal function approximation that learn mappings from input data to outputs by optimizing here a specific loss function. And we will take a very simple baby loss function because it will be so easy, you're gonna laugh about this. We apply it to physical system. They ingest observations such as trajectories, position, velocities, energy. We're going to work with some of them. And we start with a simple scalar function, a Hamiltonian or a Lagrange function, whose derivatives, to time, to whatever, yield now the dynamic of the physical system. It could not be easy. We're the first day, if you study theoretical physics at the university, this is the first day. And now we let AI do this, So, might be said to learn a function that approximates the Hamiltonian, the total energy of the system, whose derivatives determine the time evolution in phase space. So we go with a Lagrangian, the difference between the kinetic and potential energy, which to the Euler-Lagrange equation yield here the equation of motion. And you know this, and by minimizing the error between the predicted and observed dynamic using a specific loss function, like in the simplest case, the mean square error, the network will gradually adjust its internal parameter until the learned function. Yes, great. Let's be a little bit more intelligent. No, it's a little bit boring for a physicist. So, scientists, those strange people in the ivory tower, they try to recover equation from observation. Kepler looked out here to the stars and found here some beautiful equation. And now so will AI scientists. But not that they build agent, not that they have some MCP protocols or some agent-to-agent or some agent development kits by Google. No, they will use physics, law, mathematics. My goodness, this is what AI was supposed to be, Support here the human genius. Not that we humans are running behind those stupid AI systems. Come on. So we aim to uncover the underlying truth in terms of the physical equation. Let's start with the easiest one, the Hamiltonian approach. We have a canonical equations. And if you are familiar in phase space, so a phase that pairs each coordinate with its corresponding momentum. And you know this now from kindergarten. Lagrangian approach, a little bit more general. We're going to love this in 5 minutes. Define the difference between the kinetic energy and the potential energy of a system here. And the central idea is formulating using the dynamics the principle of least or stationary action. This is, if you go in mathematics and physics and you have your first university here lecture, they tell you here the principle of the least action will define from a mathematical point of view the laws of physics. And this will be the most beautiful lecture you will ever have in your life. Believe me, I enjoyed it. Hamiltonian equations, you are familiar with first order system, phase space, doubling the number of variables, position and momentum are considered. We have the symplectic geometry, symplectic integrators, Poisson brackets, you know this from theoretical physics, Lagrangian dynamics defined, Hamiltonian neural networks defined. Yes, don't be simple. So we have here the Hamiltonian MLP, the simplest thing we can think of, So we have here our hidden layers, then we have here the tangent superpolicus, beautiful, we have the forward, and then we computed this here. So we have here the auto differentiation here with torch autograd, or if you like JAX, go with here massive parallelization, which is great. And simple example, simple training loop, you're familiar with this. So great that they can do automatic differentiation. They compute here the gradients effectively using here this automatic differentiation. And this is not only to propagate the error signal backward during the training, but also to explicitly compute the derivatives that are compared against expected physical behavior. My God, physics, it's so beautiful. Loss function, you know what? We use the simplest loss function on this planet, no? Just to have here a simple idea how we can learn the laws of physics here. We have here, if you want, a certain interpretability here, because we are looking here what the neural network discovered here as a function, and then we compare it to our known physical laws. But, you know, the whole thing is not really stable, and MIT tells us, you know, training this math was really not that easy. So we have regularization methodology, suppress overfitting, encourage the network to settle on simpler, more generalized representation, and some other tricks I'm gonna tell you in a minute. Math. This is it. Easy, no? So we have here incoming a data stream here from the bottom, no? Simple physical system, pendulum, gravitational idea. So let's have a look. But now we have data from multiple systems coming in. And you know what? There's a physical law describing all three of those cases. And now we don't want that the AI just develops here one particular solution here for one, or for one pendulum, or for one gravitational field. No, find the general principle of nature. So, easy. With data stream, then we have here our neural networks. In the simplest case, we look today a multi-layer perceptron. Then we have a common layer, and this common layer, there's something beautiful happening. I'll show you in a second. And then we have it, no? So let's start. Mass receives now our observational data stream, trajectory, states, energy values, whatever we have from diverse physical systems such as the pendulum, orbital problems, or other syntactic potential that we are just dreaming of in theoretical physics. And then we have here separate neural network for each system, and they learn here a single scalar function in the simplest case that encapsulate now system-specific dynamics. A moon going around the planet Earth, for example. No? And then we have here this beautiful layer here shared across all the systems, and this differentiate here the learned scalar function with respect to the system coordinates, so either position, velocity, momentum, whatever, and infers here systems governing equation. I'm going to show you this. This enforces here the consistency of an overarching theory of all three cases across multiple systems. So, together now, the scalar function and the weights in the final layer form now the theory, and we can deduct this and have a look. Is this the right physical understanding if we just feed the input data stream to our new AI? So the idea is to unify here knowledge across multiple physical systems. So instead of training here a single neural network or whatever you like here on data from a single physical system, we have to move multi-system frameworks because they have some beautiful property I'm going to show you in about 2 minutes time. Shared final theory evaluation layer, yes, differentiation, you know this. Aggregating loss over multiple system, we can discover now a coherent theory. Training is not that easy, beautiful. Those are now the steps. And I want to, this is now important because we will have a combination of 172 d-dimensional terms that the system has to puzzle together the law of physics. So let's see. The system starts now with a learned scalar function here from each experiment. And let's say this is a Hamiltonian or Lagrangian, whatever you like. Computed now by a MLP. Then we have the automatic differentiation. We compute now the first order. This is a vector. The second order, you know, this is a matrix. Derivatives with respect to the d-dimensional input variables. And then we have two sets of terms are now defined. The vectors containing the original input and the first derivatives, all d-dimensional, and then A contains here the matrix and their inverse, d times t, clear. Now, how many different combination of products we can form? 3. We have the direct vector terms. We have a matrix from A, multiplying a vector from V, and a product of two matrices from A followed by a multiplication with a vector from V. In our case, we have 172 different candidate d-dimensional terms, and careful, we have to work with d-dimension, not d times d-dimension, collect now in a matrix T. And this matrix is now then used by the final shared layer to predict the system time derivatives, letting the network choose a theoretical formulation that fits best the data. So this is here if you want a comprehensive process to allow here the math framework to explore here the rich space of multiple candidate theories for the real underlying dynamics of a multi-physical system. Our T matrix here for J, with a set of candidate terms, represent now a rich high-dimensional space of feature. Do you remember the very old days here, BERT, the feature matrix and everything in RAG? We work with exactly this here now in mathematical terms. So a subsequent layer, a shared linear layer across all experimental nodes, takes now Tj and combines these 172 candidate terms in a simplest case in a linear way to predict now the time derivatives of x and y of the inputs. So this process allowed the network to essentially choose a way different derivative combination of our 172 candidate terms that best explained observed dynamics, therefore carving out now of the data the theoretical forms of the law of nature. Isn't this beautiful? It is so simple, and yes, we do have simplification in this calculation because we only work with 172 candidate terms here for our high-dimensional features here in this particular space. But if we will move to relativistic theory, you will see these candidate terms will increase significantly. Okay, summary. Mass as a proxy here for an AI scientist, a future AI scientist, the findings suggest can learn many diverse explanations of the same physical phenomena. But we want to learn the right one. So we have, encountering more complex systems, successful AI scientists modify the existing theories from the simple phenomenons to add more complex observation. So AI systems now modify the theory and make it more complex. We have a self-learning AI scientist, which is really interesting. And then AI scientists tend to learn similar theories, evaluated in terms of similarity of the network internal activation. You remember the last layer, we checked this. And they then they condense now either to two representation, either a Hamiltonian or a Lagrangian description of the physical system. Isn't this beautiful? The rest is gone. Very simple example, two distinct physical systems, a harmonic oscillator, a simple pendulum. Yes, you get it. We have a common structure in both systems. No? We have a restoring force that is proportional to the displacement of the object, either of the pendulum or the mass. And just find here the commonality, it finds the physical system. So the data ingestion is simply receives now the time series data for both system AI, and for the system A, input vectors representing the displacement and velocity, and here the angular momentum and the angular velocity. We have two separate sets. We have each scalar function intended to capture the energy-like quantities. Lagrangian, we have the calculation of the derivative, here the second order, and we have a unified theory evaluation by a shared final layer with a linear combination of the terms I just showed you to represent here the best underlying physics. Plus, we have a loss function, the simplest one, aggregates error from both systems, forcing the network now to adjust the parameter. So just the predicted common dynamics align well. So I want to have that this system understands both the oscillators and the pendulum observed data stream, the behavior of those two systems. And this is such a nice why we go multi-physical system. Find a common representation that works well across both systems. We have really, maybe for this time of complexity, we are non-relativistic, we are non-singularity based, we are non-superstring based, we are here in a classical physical way, maybe not even quantum mechanics. We find a law of nature. No, the AI finds a law of nature. We were so clever to design an AI that is able to do this. By the way, this AI you will find in none of the AI scientists in all the publications you find currently on arXiv. Short summary, converge to one unified theory that represents a physical principle that becomes, with an evaluation, a physical law. Great, that's it. Wasn't this beautiful? Yeah, wait, there's something else. They decided, you know what, we now add higher complexity systems. So we start here with a simple system here, a harmonic oscillator, Then we add here a simple pendulum, which give it here the data, and it should find here a mathematical law that is valid for both systems. Then, with step 20,000, we give it here a gravitational problem, no? And then we go relativistic, a relativistic harmonic oscillator. And let's just do the system that the system can learn. And you see the system starts with many configurations. This is physical theory 506, physical theory 80. The system doesn't know anything about physics, no? This is just a multi-layer perceptron. My little multi-layer perceptron has not studied theoretical physics or mathematics. So it is just trying to find something. And as you can see here, some, like the green one, seed 80 fails, no? The loss goes up, stays up. Oh, here, we have here a theory, this is the blue one, seed 96, that works for our oscillator and our pendulum, but it fails here at the gravitational well because suddenly the log goes up. So the loss function is here our primary indicative indicator, if you want. There are others, too complex for the video right now. But you see, okay, here, this particular seed 96 idea fails. And then, if we go relativistic, you have here the idea 569, in this pink, whatever it is, violet. You see, it can describe all the non-relativistic system. But the moment we go relativistic, this idea 569 fails. So you see all the different combinations that could be are simply tried out with AI. And this is where I think the power of AI is, no? As a human, we cannot go through all combinatorial possible configuration how to write here scientific laws. AI can. Interesting. As the number of the systems increases, 1, 2, 3, 4, the number of distinct terms in our mathematical description decreases. So the distinct terms learned here, so the system here at 40,000 steps, learning steps, has come up with a formula that is short and elegant. And you can apply it to all 4 physical cases, to all 4 physical systems. It's an elegant solution. Isn't this beautiful? So these results allow us to conclude that multiple scientists, if we do this here, learn the same underlying theory. Here the red and the pink line come together here. When trained on the same physical input data, the same physical system data. They converge here, and a lot of systems fail. But we have, for example here, 2 that are equal. Isn't this nice? Now, also interesting here, the systems converge, and they converge, as I told you here, for this simpler mechanical system in low dimension. The AI prefers a Hamiltonian-like description, yeah? And for a more complex system, the AI found that the Lagrangian description, this is where a lot of theoretical physics might agree, they say, yeah, the Lagrangian description is much more powerful, yeah? Especially trained on multiple, rather complex systems, yeah? Isn't this nice? Key concepts, we have talked about it. Yeah, the theory analysis, you can perform PCA or whatever you like, and you do the optimization here, whatever you want. But we already have our result. There are a lot of data in the study. Please read the study. It's a beautiful study. So this new AI scientist from MIT, not the rest, only this one, this single one, this exceptional paper here, might initially recover the dynamics resembling here a Hamiltonian, but when exposed to more complex system, morphs into a Lagrangian representation. This is done in a continuous way by the AI system, and it's simply amazing that an AI can do this. But you see, we are completely different in AI research, where the main part of AI researchers are. Main part are talking about how to build, I don't know, a web application, or how to just put one line of a sentence, into an agent, a multi-agent system, so you get created an app. This is not research. This is just how to find a nice wrapper around something. No? But here we're really down to the intelligence of the system. But we have limitations. Let's be clear. This mass framework, the training of this framework slows down more and more. The more parameter you integrate, and it becomes unstable. Even in a one-dimensional case, it becomes unstable. And this was only solved by the MIT with strong regularization and initialization technique. So this is not simple. If you say, hey, I built this in an afternoon. But you can do it. But clearly an indicator, hey, something is not optimal at this point. They tell us here, MIT, we can modify the loss function maybe further, yeah? Because we just went with the most simple loss function there is on this planet. So maybe we encourage here the learning or the unlearning of specific theory with a more advanced loss function that we use. And you saw, no, we just have feed-forward multi-layer perceptron. What about I use now a more advanced technique in AI? Convolution, attention, self-attention, cross-attention, instead of our pure feed-forward network. What if I use here more complexity for thinking about physical features in a mathematical formula? How I can build laws, how I can build mathematical representation of common ground in input data streams. Oh, I'm gonna love it. And yes, of course, as I told you, the study here by MIT was done primarily in a low dimensionality of the data. So maybe this low dimensionality is also somehow related here to the unstable training of mass. And their indicator, if you go to higher dimensionality, maybe then this unstable thing we can treat in a different way, but this would be the topic of another video. But you know, I think it's so fascinating. Don't go here with the crowd, but read those papers that are absolutely fascinating and really improve the intelligence of the AI system. And hey, yeah, if you like this kind of videos, why not subscribe? And I see you in my next video.